Hello everyone, and thank you for coming to this session. I'm Hayato from NICT, Japan, and today I'll show you the practical attacks on Nostr, which is a distributed SNS protocol. And our paper appeared at the IEEE conference, USNP 2025 today, and I focus on the implementation and code level tracing and client behavior that we didn't cover at our research paper. So this is a joint work with a member from Japanese Research Institute and University, NICT and NEC Corp, and University of Hyogo and University of Osaka. So let's start with the background. And centralized social media can change policies or sometimes moderate contents. So alternative things like Mastodon and Blue Sky, and it also Nostr, let you control your data and identity. So today, our presentation focused on the Nostr, one of the cryptographic distributed SNS protocol. So let's talk about the distributed SNS. It can follow two main models. The right-hand side is a federated model, which is a platform like a Mastodon, where different servers interpret, but identity is still anchored to servers. On the other hand, you can see the right-hand side self-serving platform model is a platform like Nostr, where users hold their own keys and no server-owned identities. In this model, the server simply reads the messages, so it means the trust shifts to the client validation from server. And this brings us freedom, but also shifts all responsibility to the user side. So that fact led us to the two questions. The first is, can a client verify public key without a central server? The second question is, do relay-based systems open new attack surface? So we'd like to answer these questions by digging into Nostr's specs and the client code verification. So I haven't introduced Nostr's details yet, so let me talk about it. So Nostr is a simple and open protocol without a central server. Users have a public key and private key pair as their identity. There are over 1.1 million user accounts, and anyone can run relay server, and users can choose any client on the application store. And it supports the public port profile, encrypted direct messages, micropayment, and also multiple device sign-in. So let's talk about the Nostr specification. And the Nostr comprises a set of model specifications referred to the Nostr implementation possible, which is called the NIPS. And among these, and four key specs on the cryptographic perspective. And the left-hand side is the real basic specification, and that is defined to the structure, event structure, and cryptographic signatures. And second spec is NIP 04, that is defines the encrypted direct messages using the key agreement by the ECGH and message encryption by the ASCVC. And Nostr also provides the delegation things, which can be used for multi-device sign-in. This facilitated multi-device delegation through a similar cryptographic structure as direct messages. And the last one is the NIP 57, and provides the micropayment. So this study presents 3 principal contributions. The first, we analyzed 56 specs and 9 clients, include the open source and or proprietary things. And we're also finding the 7 vulnerability on this. and demonstrating 8 attacks. Second, we built the proof of concept, each vulnerabilities, and we exploit it that breaking confidentiality, integrity, and availability. And the third contribution is we proposed the mitigation and worked with the developers over 2 years to report and fix these issues. Okay, let's talk about our findings. So the vulnerability we identified fall into the 3 primary categories: the integrity violation and breaking the confidentiality on the encrypted direct messages and micropayment hijacking. So they are not theoretical flaws, so they enable practical exploitation. So let's start with the 3 videos of our POC concept videos. So the first one is simply the forgery note event. So the left-hand side is a victim the screen and the Bob. And now attacker sends a forged event, and yes, the forged posted arrived at appears in the Bob's screens. So that is a very simple forgery attacks. And second one is forgery attacks on the direct messages and breaking the confidentiality on the encrypted URL. So right-hand side is attacker's terminal, and the attacker is trying to make in the forged messages. It contains the malicious attacker's URL. Okay, so waiting for the work this POC, and yes, the attacker now creates the forged encrypted message, and now it arrived at the message to the victim device. And after that, so the secret part of the URL, like authentication token, and appears in to the server attacker's servers. The final video is hijacking the micropayment. This is a combination of the forgery attacks on the direct messages, on the forgery attacks on the profile, so which is similar to the first video. The supposed Bob public profile contains the Bitcoin address, Bob's Bitcoin address. So attacker intercept it and replaces that address to attacker's address. The right-hand side is attacker's wallet. So actually, I would like to pay to the Bob's wallet, but yes, but it doesn't work, and attackers will receive the receipt, yes, Bitcoins. So that's our overviews of the root of the cause. Yes, so to understand these vulnerabilities, we need to look at the both design and the implementation issues. So a point of view, the design stage, the protocol views key is a very huge issue. And it also the malware encryption, like ASCVC, is also the very huge issues. So on the other hand, a point of view, the implementation stage. So there are common mistakes, including skipping the signature verification or incomplete re-verification, like a cache violation. So it appears the different client from the different developers. So I think the reason is the different vulnerability appears in the different client is caused by the unclear part of the specification. And I think it raised the different client to behave in the different ways, which makes these security risks going too bad. So let's move on to step-by-step tracing. So we categorize the identified attack based on the specific cryptography properties they compromised. So next slide, we walk through the concrete example and code level implementation for each POCs. So that is just a remark. The normal flow for the sending the event to the Bob. So let's go over how signature verification works in Nostr. Each event should be signed with the author's private key. In this case, I signed the post using her key. And Bob received it, and Bob verifies the event using Alice's public key. So some of you guys are wondering that whether there is any server-side verification. So actually, the specification of Nostr does not require really server to verify signatures. And of course, some really servers implementation do check signature on their side, but they do this to save their own storage from the protect from the spam rather than the helped clients. So, and also Nostr specification says server do not have to trust. Therefore, we set the target that server do not verify the signature on their side and simply forward event from sender to recipient. Okay? So, and this shows actual client implementation. That is a really simple flaw. So many clients even skip signature checks. So they do not verify signatures. So it is especially dangerous for profile events because profile has the Bitcoin address for users. So this lack of the enforcement over to invite the malicious event to spread across the networks. Yes. So, and let's see the kind of the data can make forgery based on this flaw. The data can also include the encrypted direct messages and public post and Bitcoin address for the micropayment. Yes, actually, just all of items of Nostr can forgery due to this vulnerability. So it means the lack of the verification of the signature is really simple, but it is very impactful things on the SNS. So I'd like to talk about the code level things. So let's look at something, but no signature checks at all. So many clients, especially mobile apps, with verification due to their battery life. So they accept the event without checking the signature. That's serious flaw. There are no signature checks on the code. Now, yes, I told the simply signature verification flaw. So let's move on to another things. The cache poison invest bypass the signature verification on the DAMS, which is a popular iOS Nostr client. So at the first glance, the DAMS client appears includes proper the signature verification logic, like this one. And looking at the DAMS details, we find that checks is cached before the verification. So the event cache checks in if event cache checks if event ID was verified before. So cache has the verified event. The function of the verifier returns true, and the other thing is return false and the verified signature. So that is a summary of the logic chain exposed so far. So when the event is not found in the cache, DAMS performs standard cryptographic verification. So to compromise the verification path, to attacker must gain the control of the decision point and making the return value of the verification function change to true. So if they succeed in making it return the true by injecting the fake event with the forged ID and targeting the cache entity. So and the attacker does not require breaking the cryptography. It just violates the cache. And how can we control decision point? So we can use the event IDs. Now imagine the attacker changes the content but keeps the same event ID, but same contents. So that is the content that represents the RS Bitcoin address with the attacker's Bitcoin address. So let's first break the normal communication flow, like the true contents and the true event ID. And after that, we can move the attacker's flow. When the bubble receives a fake event with the same ID that prior RS event, but the content is modified by attacker. So, okay, so then that's the Bob's device defines the cache and before it's verified result. Okay, so let's talk about the mitigation. So it's just a very simple thing. So recalculation of the event ID and check the event ID that it contains the data. And the function the calculate event ID just the hashing content. So it's just very easy things. So while the summed up the plain text integrity, so we have the verification, signature verification on the right-hand side, and we can also have the cache event. Then, so the put of them together, sometimes range bypassing can happen. Okay, let's step back at what means the distributed SNS. So in the centralized platform, the cryptographic, if the cryptographic checks the fault, the server can still help by anything like server-side verification. But the Nostr is fully self-driven system, and there are no centralized server, so a client must check their own on the device. So that is the meaning is a really cryptographic flow to the effective distributed SNS. So right now, look at the another serious issue, ciphertext integrity in the encrypted direct messages. So that is a very simple flow, the encrypted direct messages. That is the key exchanges, ECDH, and encrypted by the CBC. So as you know, so client always skips signature verification. So it just encrypt a CBC without any integrity support. So what does the attacker want? So attacker would like to change the message to the send in Bitcoin from the high. So, but they want to, but they don't have the shared key between the RS and both. So how can they do that? Okay, also let's just skip this, right? And the looking at how the CBC mode encryption enable vulnerability. In CBC mode, each plain text blocks the X word with the initial vector previous ciphertext block before encryption. So the attacker changes a few bits in the IB. They can manipulate output without knowing the key. However, that is uncontrollable for attacker because that is the output is either random things. So attacker needs to another way to forge making the messages to the given Bitcoin. So there are two types of the attackers here. So right-hand side is I told you, and right-hand side is a practical forger using the non-plain text and ciphertext P. So this is a compute simplified modification and practical forgery. So in random flipping, the attacker had no control. It's just a guesswork. But non-plain text, and they can compute the different and use it to inject fake messages. So remaining problem is how to get another plain text and ciphertext to a real-world system. So the solution is the cross-protocol attacks. I mean, we can get a non-plain text and ciphertext peer from another protocol in Nostr. So we can use the delegation protocol to get the non-plain text and the ciphertext. So that is a normal flow, and it is almost same flow as the direct messages. So between the RH device and delegation device, like a desktop PC. And in the attacker flow, attacker making the malicious QR code that has both private key and attacker's URLs. So then RS scan the malicious QR code, the malicious session between RS and Bob will start. And RS and encrypt the non-metadata using this session key, so attacker can get the non-plain text from metadata and ciphertext from this malicious session. So the takeaway of the ciphertext integrity is the first one is we must use authenticate encryption to provide ciphertext integrity. And second one is we must separate key between the different protocols. Okay, so the last topic. Last topic is breaking the confidentiality on the encrypted direct messages. So before the entering attacks, so I'd like to talk about the link preview in messaging. So many messaging apps, including some Nostr clients, support the link preview. And the link preview automatically fetch web pages metadata when the messages include the URL. So there are two types of the method, client-side generation and server-side generation. And now, in this presentation, I'll focus on the client-side generation. And so what kind of the problem can it cause? The client-side generation, link preview generation, can be further divided into two types. The one of is the sender-side generation, and the other side is the receiver-side generation. A well-known issue is that the receiver generation preview, the IP address can be leaked. It means that it can be the privacy issue, but it's just there are no confidentiality break. So we think, can this behavior actually help attacker, and recover the plain text on the encrypted direct messages? So can attacker still run the plain text even if the encryption algorithm is strong and safe? So in the capture the flag like a security competition, we usually see the padding worker attacks using error, overtiming, leaks, data, So we ask, do real-world messaging have the features to react to decrypted content in visible ways? The answer is yes. We can use the link preview as our code. So let's look the attacks on the secret URL. That is contain like a invitation for the online meeting or the shared link for the cloud storage. So here is how attacker works the technical level. And after decryption, the Nostr client sees the URL and try to preview it. And the first attacker observed the DNS materials request to get the domain part of the encrypted URL, like example.net. The attacker never decrypted anything in this part, so they just want to the response. So now the attacker takes the step further using CVC vulnerability, the flip bit of the ciphertext to change the URL domain and from the example to the emu.test. So when the victim receives the modified ciphertext from the attackers, the link previews files to their attackers' servers. But this modified URL has the secret part of the URL, like a secret token for the meeting invitation. So from the access row on the server, attacker's servers, attacker can get the secret part of the URL. And so far, I've shown how the attacker can steal part of the URL, like a token. But what if they want to more? So what if they want to throw messages around the URL? So let's explore how to do the next. Right now, to consider different angle. Instead of using the preview, recover known URLs can be recover known plain text outside of the URL. So the let's say the attack know the message status like HTTPS, but they don't know the first 3 bytes of the messages in this case. So they flip byte in the IV first and the third byte to be the H. It's just like a 1 byte brute force and using encrypted message forgery. If the client should had the H in the decrypted messages, the preview and fire to the attacker's servers. So the attacker can guess the timing of the client has the 3 byte as the H. So attacker can repeat the and apply to the second byte and first byte, and the final attacker can get all of the plain text around this URL, encrypted URLs. So that is the takeaway, and that is the same as Ciphertext integrity. Okay, I'd like to talk the 3 takeaways all of this presentation. The first one is that decentralized architectures tap the risks and overs. So yes. And second, the takeaway is about the real attacks and how to stop them. So we showed these attacks and the fake and profile and impersonation, and changing the encrypted DMs using the CVC vulnerability. And the URL and token risks through link previews. And also the plain text recovery using Oracle-like behavior. The problems are not just encoding mistakes. They come from the bot design and implementation. So our results shows that strong cryptographic algorithms are not enough. So we need to making the secure codings for the cryptographic implementation and the cryptographic system. So the third takeaway is how can we design the safer decentralized system? So in centralized systems, fix can be deployed quickly, But in the decentralized ones, many clients developed by the different communities. So it is difficult to fix the vulnerabilities at the same times. So we need to get the design right from the start. So that means clear rules for the signature checks, not just assign it, but how to verify it. That is a very, very important thing to the specification to be modified, to be updated. The second item to improve it is the key separation. So client must use the different keys for the messaging, identity, and delegation. And such things is have to update is the zero trust. The client must verify everything, even from the any event from the anywhere server. The rules help with the protocol where we replace trust. And yes, so that is a very important thing. So I would like to repeat. So the update, the distributed SNS may take more time than the centralized ones because they are independent real administrators in their so many server implementation, and there are so many client implementation from the different developers and different communities. So that is a summary of our works. So this was the first full security analysis of Nostr, covering the cryptography and implementation flaws. We showed many clients skip the signature checks, or it can be bypassing using the client-side cache. And malware encryption, like a CVC mode, let user change the ciphertext. So we need to use the message authentication code or authenticated encryption to provide integrity. So the sometimes important things, so outside of the cryptographic things like a link preview. So receiver side link previews with the private URL and the token and messages when ciphertext can be modified. So we also showed the fix and design tips. So that is a very important thing. The takeaway is the strong cryptography things is not enough. We need to good code and a better cryptographic protocol design to making a decentralized system secure. So thank you for listening. So we have the academic paper. It appears in the IEEE USNP conference. So you can check the more detail, a point of view the academic side. And you can also check our website to summarize of our works and relevant URL. And you can also find our contact point from our website. Thank you for listening. So you can ask me anything after this session. Thank you.